All right, so at this point we've talked about confidence intervals. We've talked about hypothesis testing. We can talk very briefly, I mean one slide brief, about the sort of relationship between them. So this sort of should be kind of an intuitive idea. You can equate a two-sided hypothesis test with a significance level alpha to a 100 times 1 minus alpha percent confidence interval. So making it a little less jargony, a hypothesis test at the 0.05 level would correspond to a 95% confidence interval. A hypothesis test at the 0.10 level would correspond with a 90% confidence interval. And the way that you kind of relate these two things is this, that if the hypothesized mean is in the confidence interval, you fail to reject the null hypothesis. And if the hypothesized mean is outside of the confidence interval, you reject the null hypothesis. So if you think about that should be intuitive, right? So if you have a null hypothesis that the mean fat content for Big Macs is 30 grams of fat, and you do a confidence interval, I mean, we're really kind of interested in whether or not 30 is in that confidence interval, right? If 30 is not in the confidence interval, well, that means we should reject the null hypothesis. If 30 is inside the confidence interval, well, the null hypothesis then is plausible, right? And we would hence fail to reject it. Excuse me, very rude. So hopefully that makes sense. We're going to move on from there. And we're going to move on to kind of some of the extensions. So we talked a lot about kind of what we might think of as univariate inference on a single sample. But often we're interested on instead inference on two samples. That is, we're interested in testing whether or not two groups are different with respect to some parameter of interest, typically with respect to their means. That is, maybe two groups have different population means. So examples, right? We might be interested in whether or not men and women have different mean levels of cholesterol. We might be interested in whether or not two different industries have different levels of stock growth on average. We might be interested in whether the growth rate for a new fertilizer is better than an old fertilizer, right? Or whether some sort of new drug is better than some old drug, some placebo drug. So these are the types of questions that we might kind of explore, and I think are sort of natural extensions of kind of the work that we've already kind of been working on. Now, how do we do this? Well, if we want to compare two populations, we take a sample from each of the two populations. And then kind of what we do with that sample depends upon which situation we're in. So we could be in one of two situations. We could be in what's called the dependent situation, in which case we would do what's called a dependent t-test, or maybe a little bit more commonly a paired t-test. Or we can do an independent t-test. So let's kind of look at each of these. A dependent t-test is the situation where each observation from the first sample can be naturally paired with an observation from the other sample. So the classic example would be like pre and post tests, right? So a person takes a test at the beginning of class. They take the test, same test or a similar test at the end of class, and you hope that their score went up, right? So you're looking at the difference in scores. Now that's the most common example of dependent, but in theory you could have like husbands and wives paired together, you could have twins paired together, you could have observations from a person's left hand and a person's right hand, and these are sort of paired observations. So anytime you have paired observations, one observation from each pair in one of the two samples, this is kind of a dependent framework. Because right, in every one of our samples you have an observation that depends upon, right, an observation from the other sample. Now, the independent scenario is where there is no relationship between the sampling processes used in each group. That is, every observation in sort of group A is independent of all observations in group B. Now, a little bit of a typo there, I guess. I'm not sure what I meant by completing. Maybe I meant to say we're interested in testing, assuming a two-sided test, the following competing hypotheses. The null hypothesis is that that the mean from group 1 is equal to the mean from group 2. The alternative is that those two means are not equal to one another. Now note that this could be algebraically sort of simplified or algebraically shuffled. If we subtract mu sub 2 from both sides of those equations, then we get sort of these quote new hypotheses. That is, mu1 minus mu2, the difference in means equals 0. The alternative being the difference in means is something other than 0. Writing it in that second framework gives us a little bit of insight into what our test statistic is going to be. And we'll talk more about that in just a few slides. Now, we can take that mu1 minus mu2 and we can just call that mu sub d, the mean of the differences. If we're working in the dependent framework. So actually what we see here is that we're working with dependent samples. It sort of simplifies into kind of the univariate case that we already talked about, right? So what do we basically do? We have two observations for each individual. We have these paired observations, but two observations, right? So we reduce these two observations into a single observation by looking at the difference between them. So instead of having two scores for a student, right, their pre-test and post-test, say maybe they got a 60 and then a 70, we actually give them just one value, which is the difference in scores, and that one value would be 10. That's the difference in their score. Their score went up by 10 points. And so instead of that, we now have, for every student, we have the difference, how much their score went up or down, and we're interested in testing whether the mean of these differences is equal to 0 or not equal to 0. So this just becomes exactly like the type of problem we've already learned how to tackle, which means that we're done and done. Well, I guess not quite, because we still have to talk about the independent framework. As I think what I just said, we use the mean of the differences as the basis for our test statistic, and this just simplifies into what we already talked about. This is called a paired t-test. Now in the independent situation, we still use the difference in sample means as the basis of our test statistic. So, right, that makes sense. We're really interested in testing mu1 minus mu2. So what would be like our best test statistic? Something based off x bar 1 minus x bar 2. And so that becomes kind of the crux, the cornerstone of our test statistic. The test statistic, of course, will give us our p-value. The p-value, of course, just as it always does, will lead us towards our conclusion. Now, I'm not going to get too much into the formula, so I say that x bar 1 minus x bar 2 is kind of the foundation of our test statistic. I'm not going to give us the whole formula for the test statistic. The formulas are a bit on the complex sides. There's different types of formulas depending on whether or not the two populations we're willing to assume that they have the same or different population standard deviations. So sort of two formulas, each one's pretty complex. This is kind of the usual, I think, transition point from the kind of relatively simple intuitive formulas that we've seen in the previous PowerPoints to more complex formulas that are best sort of handled or tackled by software, right? SAS can handle these formulas, knows these formulas, and can implement them for us using proc t-test. Overall, the process is called an independent t-test. So here's how we would do it in proc t-test. So here's a serial data set. I think we used it a couple times in Stat 511. And so what do? We have two cereals. Some of the cereals are low calorie cereals. Some of the cereals are not low calorie. So these are our two groups. We have a low calorie group and a non-low calorie group. So those are the groups we want to compare. And the variable we want to work with is carbohydrates. So we want to test the null hypothesis that these groups, these low calorie versus not low calorie cereals, whether or not they have the same average carbohydrates. Are the carbs the same between these two groups? So this is the syntax. We have proc t-test, our variable that contains the groups. We put in a class statement. The variable that contains the actual quantitative variable we want to test goes into the var statement. And then here's our output. The output's kind of structured like a little bit strange. Well, the top is nice. So the top will give us a little bit of kind of descriptive information. So in particular, it says that the average number of carbs for non-low calorie cereal is 14.9. The average number of carbs for low calorie cereal is 14. It tells us how many cereals fall into each category, and it even tells us what the difference between these means are. So the difference is not quite 1 unit of carbohydrates, right? Whatever the units of carbohydrates are. Joules maybe? Or I don't know, I'm pulling that from my brain. I could be completely wrong, but right, 0.9 units. The difference is about 0.9. Now, is that a significant difference? That's the question that we're interested in. And to kind of answer that inferential question, it's kind of a little bit backwards because we kind of work our way from the bottom up in terms of reading through the output. So the actual first thing that we look at is the very, very bottom where it says equality of variances. And that line there is testing whether or not the variances between the two groups are the same or whether they're different. Because that will tell us which of the two types of t-tests to do. Now, the null hypothesis of the equality of variances test, the null hypothesis is that the variances are equal to one another. So if we go all the way to the very end, we see the p-value. The p-value in this case is 0.1193. 0.1193 is more than our usual cutoff of 0.05. And so that means we fail to reject the null hypothesis. There's not enough evidence for us to conclude that the variances are different. Hence, in a roundabout way, we're gonna say that we're gonna move forward under the assumption that they're equal. So then we could go one more step up, right? And if we go one step up, there's actually t-tests being done. There's two different t-tests. One of the t-tests assumes equal variance. One of the t-tests assumes unequal variance. We decided that we thought there was equal variance, so that's the test we should be using. The p-value for that test is 0.3733. So again, using the typical 0.05 cutoff, we would fail to reject the null hypothesis. That is, we don't think there's enough evidence at the 0.05 level. There's not enough evidence to conclude that the mean carb content is different between the two groups of cereals. That is, we don't think the means are different. Low-cal and non-low-cal cereals, on average, are the same in terms of the amount of carbs or carbohydrates. Pretty straightforward, right? Now, that wraps up all of the review material. As a final check, I've put up a review lab in addition to the lab solution. So this is kind of intended to be done entirely in SAS. So a SAS lab and SAS solutions that touch on all the different things we've talked about throughout this parade of PowerPoints. You should do these labs and solutions. You should go over them before the start of the spring semester, and you should come to myself or the GAs ASAP with any questions you might have so that you can start your 512 semester on the strongest possible footing. All right, I'm not sure how long it is between when you're listening to this and the start of that semester, but I gotta tell you, I'm really looking forward to it, and I'm really looking forward to seeing you again in the classroom. So, see you then.